So, introduction to programmable logic controllers. This is going to be an introduction to electricity. Some of y'all might already know all this stuff, but odds are there's some little things in here that you probably didn't know. So, pretest. What is an electrical circuit? What is a programmable logic controller? What is a conductor? What is an electroinsulator? What natural metals are? What natural metal is the best conductor of electricity? What are the two most common used electrical conductors? What's voltage, current, resistance, and power? What is the basic difference between DC and AC? What is cycle, frequency, and hertz? We need to learn a little about that. Some of y'all hadn't had AC. We need to know the difference between an electrical short and electro open. This is probably one of the most misused terms. These are probably one of the most misused terms in non-people that don't know the trade. What's the basic requirement for electrical circuit? And we'll need to learn about series parallel and series parallel circuits. So this is the best conductor of electricity. Most people think gold is, but silver is actually the best conductor of electricity. We usually don't use it we use it as a plating. Usually on light switches and relay contacts and stuff like that. Anytime where we make a connection just by touching things together, we like to coat those with silver. Basically, the most widely used, one of the most widely used, of course, is copper. Gold is very good. It's not as good as copper or silver, but the advantage of copper, silver oxidizes or rust. We have silver rust. Silver rust is a really good conductor, but it gets on things. Copper oxide or copper rust, this is an insulator. And it's that green stuff. So most of your power lines, when they get down pretty close to your house, these are copper on the power lines, not on your down drops. And but they look green. They look green, or they don't look because they're oxidized. And a lot of people don't understand that the outside coating of the Statue of Liberty is copper, but it looks green because that's copper oxide. In fact, when they redid the coating, when they rebuilt the Statue of Liberty, they literally had to spray salt water up on the statue to make it oxidize again and turn green so everybody would recognize it. Aluminum, this is a good conductor. It's not a very good conductor, but it's a good conductor. But we usually use this for high voltage electrical conductors, and hopefully we'll find out a little bit why we can do that. Copper and aluminum are by far the most widely used electrical conductors out there. So force, this is physics. Force, any interaction that attempts to change the motion of an object. Work is when we transfer energy from one form to the other. To get work, we have to have some type of force, and we've got to have some type of motion, guys. So basically, one of the formulas for work is how much force and how much distance does the object move relative to that force. In power, or in electrical, we call this power. We call our work power. And this is voltage, which is our force. We'll talk about that. And current, which is what's actually in motion. So the way we calculate electrical work is we take the number of volts that's causing the push, and how fast the current moves because of that foot push through some type of load. So this is our formula, by the way. So electromotive force or voltage. So these two terms are interchangeable. They're used mean exactly the same thing. Is a difference of electrical potential that forces electrons to move. So voltage is the force, electrons are moving, and that's the speed. Voltage in formulas, voltage is represented by either V or E. It depends on what book you read it in. What most people don't like is when we have an equation, they don't want V on the left, and your answer's got a V on it. So a lot of people will use E for voltage and V for volts, and we'll talk about that in a minute. Current, this is the flow of electrons that is the result of a difference of electrical potential. And of course, resistance and reactance, these are the opposition to flow. So we got to get work, we got to push against something. So devices that have resistance, these are the devices that are actually doing the work in the circuit. We won't talk much about reactance in this class. It's not necessary to know. But reactance occurs with alternating current. It doesn't occur with direct current. So when you take AC, or some of y'all had AC, y'all know that we have to understand reactance, because reactance appears to do work, but it don't do work. Resistance is actually the only thing in a circuit that actually does the work. So all electrical devices operate off electrical current. The amount of power produced by these devices is determined by the amount of current that flows through the devices and the force that is causing it to work. So to get work, we have to have a force, and then we have to make things move. So if I come up here and I push against the wall in this room, I'm not doing any work. Even though I'm generating a force, if that wall does not move, I'm not doing any work. So to get work, we have to have a force, and when we generate that force with a pressure, when we generate that force, then something has to move to get work. So if you sit on your rump all day long playing games, you're not getting very much work done, right? Tapping on your phone or your tablet. The amount of current is controlled by the amount of force divided by the opposition in the circuit. The strength of the difference of electrical potential, or EMF, and the amount of opposition to the flow resistance determines the speed at which the electrons move. So what we're literally doing is we have a material that, like certain materials, want to give up electrons. And if we come up here and we put a difference of electrical potential across those electrons, it causes these electrons to move. And of course, that the motion is moving through resistance actually creates work. Some materials, such as most metals, allows electrons to move freely, while other metals, such as rubber, do not. For this reason, most metals make, not all. We have like tungsten and stuff like that. We do have some metals that have a pretty good deal of resistance, and these are usually the metals that's in your electric heaters, in your stove. If you've got an electric stove up there, that's what's causing them to get hot, because they've got a resistance in them. And then, of course, if you push current through resistance, one of the byproducts of watts or heat work is heat. Make good electrical conductors, and then rubbers, plastics, ceramics, glass, Teflon, and air make a pretty good what we call insulators. These are devices that don't want to allow current to flow through them. What determines, but the problem is that a lot of people don't understand that everything has opposition. Everything has got resistance. So this is why sometimes when you have a short circuit in your house or somewhere, the wire actually turns red and burns up, because the resistance of the wire. What determines how much resistance your conductor has would be what it's made out of. So silver would have very little resistance per length. The physical size of the wires. So this is why the wires running from the downdrop of your transformer down to your house are a pretty good size, because they got to handle a lot of current that supports your whole house. But then you get into your extension cords and stuff like that. Those are not have a lot smaller size, because they're not having to conduct as much current. Plus the length, and then the temperature. The temperature varies the opposition. So we have volts. This is the measure of the force used to push electrical current. We have amperes. Most people call it amps, and most of y'all seen that. There's a lot of devices, especially like vacuum cleaners and stuff like that are rated in amps. Is measured. So 1 ampere current means somehow we're causing 6.25 times 10 to the 18th electrons to move past a point in a circuit in 1 second. So if you got 8 amps of power, that means that would be 8 times 6.25 times 10 to the 18th moving past a point in a circuit in 1 second. So these things are moving really, really fast. pretty close to the speed of light. And that gives you the number out there. And I think this was done mathematically with physics. There was nobody that actually counted this because they would still be counting. But in mathematical formulas, we use I to represent current, the amount, and then we use, and then amps are the actual unit. Resistance and reactance are the measure of the amount of opposition to the flow. The unit of opposition is what we call ohms. All devices exhibit opposition to flow of current. Conductors have almost no opposition, while opposition of load is considerably high. Insulators have extremely high opposition. So there's no such thing that has infinite ohms, even though when we put a meter and put it on ohms and it comes up and says overload, it doesn't mean there's no resistance there. It just means the resistance is so high that your meter cannot measure it. We have a unit called a megger, which gives us the ability to actually measure the resistance of insulators. But it's so high that there's almost no ability for current to flow through them. So we have a law called Ohm's law. This shows us the how we calculate these things if we know certain values. So over here, this could be E. So you see some books teach E. Here at Lawson State, we teach V. But your answer is V too. So mathematically, that's not correct where you have V on the left side of the equation, you have V on the right side of the equation. So this is why a lot of books teach E for voltage. So it says, and we don't have to know this, it's just us talking. So if I know the amount of voltage in the circuit and I can measure the amount of current, then I can calculate the amount of opposition. If I know the amount of voltage and I know the amount of opposition, then I can calculate the current in the circuit. So they're all proportional to it. So if you don't change opposition and if you double voltage, you're going to double current, and it's just that simple. If opposition don't change. Watt's law. So what we do is our power we rate in a unit called watts, or volt amperes, which we won't talk about in this class. So AC, we'll learn about another unit called volt amperes, but we're not going to talk about this in this class. So watts. So when you get your power bill every month, or you go online and look at it, a lot of us don't get paper bills anymore. We have an account set up on these different places where we go, but you can always go and look at your bill, and it's going to be saying, okay, you use this many kilowatts or thousand of watts per hour, and that's what you pay for your power bill. You pay kilowatts per hour. This is the way we calculate power. If I didn't accidentally went through there. So the amount of power, this is the way the power company calculates that, is your voltage that they give to your house times the current. And what we see is, this is a very, very important formula right here, that the amount of current flow that we have is the power divided by the volts. And this is what Alabama Power is using, because if everything has a resistance, that means wire has a resistance. And V, how much voltage we drop in our wire, is equal to I times R. So the resistance of the wire is set by the material, it's set by the size, it's set by the length. And once you put that out there, of course, you can't change it. Of course, this is why if you look at the wires going to your dryer, they're probably bigger than the wires going to your washing machine. The washing machine usually requires less power. If you go out and if you got an electrical HVAC system, you'll go out and look, that's going to have a pretty good size wire going out there. But the problem we have is that once I've set a wire, then I would determine how much, your power company calls it line loss. How much push do you lose in your lines, in your conductors? Well, what they found out a long time ago is that the amount of voltage drop we get is the current times the resistance. But according to the power formula, it says I is equal to P over V. So Alabama Power is not trying to sell you current, and Alabama Power is not trying to sell you volts. It's even in their name, they're selling you power. So what that means is the higher I make this voltage, the less current that's going to be required to transmit that power. So that means if I was going to try to give you a 1,000 watts of power at 1 volt, then it would take 1,000 amps. If I was going to give you 1,000 watts of power at 1,000 volts, then it would only require 1 amp. So what that means is if we can make the voltage real high, then we'll have less loss in our lines. So what that means is we can step the voltage up and down with these devices called transformers. So up on your power line coming into your transformer, good gracious, that's, probably around 20,000 volts. But when they go through that transformer and they step it down to 110 volts, then it becomes safer, but the current's got to go up to deliver that same amount of power. So they step up the voltage real high for transmission, and then they step it down for safety. So this is something that we can do with AC that we can't do with DC, is we can step it up and step it down with transformers. And I'll show you all a basic transformer when we come into class, and it's really cool. So electrical circuit is a complete path for current to flow. It consists of a voltage source. It consists of a source conductor, a load, and a return conductor. DC, the source conductor and the return conductor doesn't change. Alternating current, they're constantly swapping. Most electrical circuits also include at least one control device. So your house, you have a light switch. So that would be considered what we call a control device. So if you understand the human circuitry system, you're okay. So your power, your source, your voltage source, this is very similar to your heart. Your heart don't move. All it does is create a difference of potential, which causes blood to flow. Your heart does not make blood. All your heart does is make the blood that's there move. It's just like conductors does not create current. All the electrons is there, and what the voltage source does, it creates a difference of potential to cause that current to move. So it's all there in all the devices. Then we have blood vessels or veins. This takes it from the heart and transmits it out through the muscles. The muscles use all the nutrients and the energy from your brain, from the blood, to be able to create work. So if you understand that, then you have a basic feel of electrical circuit. So the heart creates a difference in pressure, pumps blood out through the arteries, through the muscles, and then pulls the blood back to the veins, right? Voltage is similar to the heart, so the voltage don't move. Even though a lot of people think it does, voltage don't move. We can cause loss of push by going through different devices, but the actual voltage source does not move. It's back at the source. So that's like your heart. Your heart does not move. That's your source of your pressure. But it doesn't mean that you can't have loss through your system, right? So we have what we call blood clots and stuff like that, that could cause, we have a drop in pressure through that. Electrical current is similar to the flow of blood. Electrical conductors are similar to the vessels, and the muscles are similar to the loads. So if you understand that, then you've got a pretty good feel of what a circuit does. So this is a basic electrical circuit. So this is probably going to stop. This is the symbol of a DC voltage source. So DC means current flows in one direction. So these are produced by of course, batteries. These are produced by power supplies, DC power supplies. This would be the same symbol, by the way, not only for a battery, but it would also be a symbol for an electronically DC power source. So when we get our DCs operate, a portion of our PLCs operate off of DC. We don't have any batteries inside. We have a DC We have a power source that converts AC over to DC. And you see these all the time. So these little old cubes and everything that you have, you plug them into power, Alabama Power or TVA, and then they output DC on that USB A connector. So, but that would be, we would use this same symbol for that little brick that you plug in, the little cube that you plug into your power outlet, or your laptop computer, or any type of thing that we have a charger. A lot of times, like on TVs now, used to, when TVs were bigger, the power supply was actually built in the TV itself. But even on these LED TVs that are so thin, you actually have an external power supply now that you plug into the back of the DC, so you can actually see the DC power source. So there's the voltage source. This is the source conductor, and this is the return conductor. And then we have a switch that allows us to stop the current or let the current go. So this is a perfect example of exactly what you're doing when you go in and flip a light switch in your house. There's a lot more to it on electronics now. Most of your electronics are never really off. They're in standby. So even when you hit that little button on top of your cell phone, your battery still goes dead sooner or later because it's not actually off, it's just in standby. A return conductor, so these never change. So these are basic circuits. We have a basic circuit or a single load circuit. We have these in programmable controllers and also motor controls. We use the same size for motor controls. We have a series circuit. These are not used in PLCs. We have a parallel circuit, which we'll run into in PLCs, and then we have series parallel circuits that we don't have in PLCs. So the only two circuits that we're going to deal with is a basic series circuit. These are going to be single load circuits. Excuse me. And parallel circuits. These are the two that we'll do. And somebody in here will try to do a series parallel circuit. So this is a series circuit, a basic series circuit, a single load series circuit. Let me know that I've got the lecture paused, so I won't be actually recording the lecture. So the only two circuits we have to work with when you're in DC, if you take DC, some of y'all have already had it, then you'll have to deal with series circuits, you'll have to deal with parallel circuits, and you'll have to deal with series parallel circuits. And when you take AC, you'll have to do that. But in PLCs, basically, we have just these simple circuits like this, one load and then a voltage source. So one direction. Multi-load series circuits, we don't have these in PLCs, but this would look like this. This is similar. The problem we have with series circuits like this, if one of your loads go bad, then everything dies. So most people's got Christmas lights, and you notice one of the bulb goes out, and you'll lose a section, and that's because they're all hooked in series. So we don't run into these. You'll run into them a lot in electronics. So you'll learn how to do this when you take DC. You'll learn all the math and everything for it. Parallel circuits. This is the way the load applied to each load is the same. All the loads are connected across the voltage source when all the control devices are true. The current is distributed inversely proportional to the opposition. So this is a parallel circuit. This is what you have in your house. So your whole power grid in your house is wired in parallel. So what we can do is I can remove this load right here, and it doesn't affect the other loads. It causes the total current to go down, which means your power bill goes down, but it allows us to add and remove loads without affecting any other load. So you can turn lights off and your refrigerator stays on. You can go in and plug in a vacuum cleaner. If you unplug it, nothing else has that problem. So we have parallel circuits, definitely have parallel circuits in program controllers and also in what we call relay logic or relays. And we'll look and see what relays are. So these are the two circuits that we'll learn how to program and also how we will wire up devices to the PLC. and we'll get devices out. PLCs are nothing but computers. This basically has three main parts. It has the inputs, and then we run this into, of course, the computer, and eventually we're going to generate an output. And these are computers. So your cell phone, you got inputs. So you got your touch screen. If your touch screen goes bad, what do? You throw it away, or if you're lucky, you can take it and get it fixed, and it won't cost, especially if you got insurance on it. But usually that insurance isn't good because most of the things you break on it are not covered. And then eventually you're going to have to generate an output. So right now, this is my input, and of course my output would be that popping up on the screen. So we'll look at how do we connect inputs to the PLC, how do we connect outputs to the PLC, and of course the computer does one thing, it runs programs. Which we call apps, applications. So y'all understand apps. So that's what we're going to be doing this semester. We're going to be writing applications or apps for our PLC to run. And we're going to use a programming language called ladder logic. But we'll look at several. Series parallel, this is the way electronics are wired. This is the way most Christmas lights are wired in series parallel. So what happens is you'll lose a light and just a section will go out. That's the sections that are in series, but another light section will stay on. Used to, Christmas lights were totally series, and you'd have the whole string go out, and you'd go find a good bulb, and you'd go all the way down through the thing, replacing the bulb to see when it came on. Control devices controls the flow of current and produces no electrical work. So they don't have opposition, or they have almost not. They have an opposition so low we can't measure it. So light switches are not supposed to get hot because they have no opposition, which means they have a function in the circuit, but they don't produce power. The connection of control devices does not determine if the circuit is series, parallel, or series parallel. So we can connect control devices any way. What determines what type of circuit it is how we connect the loads. In PLCs and motor control circuits, we either connect them in a one load circuit or parallel. So switches, push buttons, sensors, relays, all these would be considered input devices. So this is a control device right here. So we're doing this to control the flow. And y'all should be very familiar with this because every house has these. Where you go in and you can turn the lights on or off, or you can turn your stove on or off, or you can turn your heating system on or off. And your heat comes on and your heat comes off, so there's got to be some automatic control device in there turning your heater on and turning your heater off. And this is where we'll get into what we call sensors a little bit in this class, and the different type of sensors, that's electrical sensors that we have available to us. So switches, push button, relay contacts, and of course sensors. And electrical sensors does the same thing that your senses do, and that's to convert a physical stimulus into some type of electrical equivalent so your brain can process it. So these are push buttons. These are most of the type of push buttons that you see in industry. Push buttons in industry are usually very large, so people that's wearing gloves can operate them. So we have different types of sensors we'll look at. We have what we call contact sensors. These are guys that's going to have to make physical contact with what they're designed to measure. So we'll look at some of those. Then we have what we call non-contact sensors. So these are sensors that can measure things without making physical contact. So when you come into campus, the guy's either a security guard or a campus police is going to measure your temperature, and they're not going to touch you. So that's going to be a non-contact sensor. But if you get these mercury or some of these temperature sensors, you literally have to stick them in your mouth or under your armpit or other places we won't mention. for little babies to measure their temperature. So contact and non-contact, we'll look at those. So these are guys called limit switches. These are definitely, and when we come into campus, what we'll do is we'll look. We got two manufacturing lines. We got an Amatro line, and we'll show y'all some limit switches on this line. These are mechanical devices, so they sense when something is at a certain spot or location, and then of course the device has to make physical contact with these operators. So we'll come up here, we'll show y'all some limit switches. So both lines, we have an Amatro line and we have a Festo manufacturing line. And one of the things that we'll do when we start class and come on campus on the 16th is we will come up here and we will identify every sensor that we're going to show you on these slides. And both manufacturing lines use these sensors. Proximity sensors. Proximity sensors, these are usually classified as non-contact sensors. So we have these sensors that we'll look at, and we have the ones that we have available to us. We have what we call inductive sensors. These guys sense the presence of metal, and y'all probably ran across one of these sensors when you go out driving. These are the sensors that are buried out there under the road that determines when the traffic lights change. Those are inductive sensors, and what they're doing is they're sensing the metal in your car. We had a problem with the inductive sensor going out the campus gate, in that when I rode my motorcycles didn't have enough metal in them to switch it, because they had set the sensitivity to look for cars, not motorcycles. So I had to, if a car pulled up behind me, I was okay. But if a car wasn't behind me, then I'd kick my kickstand down and I'd walk over and press the pedestrian walk thing to switch that. So there's a sensitivity adjust on a lot of these sensors, so you can make them inductive. You might want it not to see copper, but you want it to see steel. Most of these sensors, you actually have what we call a sensitivity or a threshold adjust. Capacitive sensors, these guys will connect, we can design these to detect almost anything, solids or liquids. So if you brought your finger up against a inductive sensor, you would not trip it. But if you brought your finger up against a capacitive sensor, it would actually trip it. So we have capacitive sensors, we have inductive sensors. Reed switches, Hall effect, and magnetoresistance, these guys detect magnetic fields. And we'll show y'all where this comes into play. So we have these on our manufacturing lines. Photoelectric, these guys are going to either break or allow a light to pass between a transmitter or receiver, or it's not. And we'll show y'all those. Both of these lines have extensive use of photoelectric sensors. Ultrasonics, we have ultrasonic sensors on both of our lines. So we'll look at those. We use ultrasonic sensors to sense, most of the time we use it to sense position. On the Amatro line, it's actually used to measure the height of the item that we're trying to manufacture. And if it's not between set limits, then we'll reject that, and we'll show y'all that when we come on campus on the 26th. So we're going to show y'all actually PLCs in action. We're going to show y'all the PLCs that you're going to be using. We'll come in and look at our manufacturing lines. We'll identify the sensors, and we'll look at inputs and outputs and stuff like that on the PLCs, on some of the stuff that we're going to talk about, while we're in our virtual classroom. So I've got cameras set up, and I'll show y'all some of the stuff. In fact, I don't have my camera set up for the Festo line, but this is the Amatro line right here. So the units down in the bottom, these are the program logic controllers. These are Siemens PLCs. This is the actual DC power supply, if I can get in front of the camera. That's converting Alabama Power, or here we go on TVA, over to direct current. And of course, these are some of the push buttons that we have. E-stop, power switch, and some of the push buttons. And notice they're industrial grade, so they're big, so people can operate them with fingers on there. And of course, we can't get into this, but what we'll do up here in the actual manufacturing line, we'll show y'all all these sensors. In fact, you can see one of them up here blinking at you. That guy right there. So it's actually saying I don't see anything right now. So most of them have an indication that we can look at. And all these sensors are connected down to the PLCs down here. And then we run a program. So these lights on the PLC, these are telling us a lot of things that's going on, and they help us troubleshoot a lot, and we'll look at those and we'll explain those as we move. So the Amatro manufacturing line runs Siemens PLCs, and then the Festo line, which is down here, this runs Allen Bradley PLCs. And the objects that they made actually tie together. We do have a Siemens PLC, so in ILT212, you'll get to attempt a certification on Siemens PLCs. It's available to you. But what we do on this one is we convert the programs written for Allen Bradley over to Siemens. So that would be similar to taking an application that's been written for an iPhone and converting it over to a what's the other one? Skip my brain. The other phone that runs the other operating system. What's the other operating system for phones? I have an iPhone, so Samsung. That's the name of the phone, but the operating system. What's the operating system? It's put out by Google, and it's free. So it's got a name. My brain went dead, guys. So push buttons. These, and I'll show y'all one of these. These are relays. So relays are electrically controlled switch. So electrically controlled switch. This allows us to do things. It allows us to touch a little button on my steering wheel to turn on my lights on my car. Well, if you went out on your hood and you opened it up, there's a big old black box out there. And if you pop it open, it's got a bunch of relays in there. So what happens is when you tell to turn on your lights, it's going to be a little tiny switch that cannot control. And some cars have push button starter buttons on them. So you have your fob that you carry around. You don't have a key. You just have something you carry around in your pocket, and then when you get in your car, you press a button, and the thing starts. Well, the starter, which is pulling, quite a bit of amps, hundreds of amps to start that car, that you're not doing that. So what you're doing is your push button is energizing a relay, and then your relay is closing contacts that are connected to the relay. So this is all done by magnetics, and we'll show y'all these when we come into campus. So it allows us to have low voltage, like 24 volts, running the coil, but the contacts can be hooked up to 240 volts. So you can use relays to change the voltage level or even the type current. So the electromagnet the coil can be a DC coil, but you can switch AC. So these are very, very, very popular in control industry. So the PLC cannot run 100. The output of a PLC could not run a 100 horsepower motor, but it could pick up a relay, and the relay could run the motor. So we run into these all over the place. I'll show y'all relays over all these manufacturing lines. I don't think we can see one from here, but it's got several motors and they all have relays. So the program controller energizes the relay, and then the relay runs the motors on the line. So we'll look at that when we come in. So basically solenoids, these take electrical and like I'll have to bring that in. I'll show y'all next class. This just creates an electromagnet, and I'll show y'all that, which causes a plunger to move. And then we can connect things to plungers. So if you ever been to a building where they have to buzz you in, well, what they're doing is they're coming in and they're energizing the solenoid, and the solenoid unlocks the door. Your washing machine, it has two solenoids that's controlling the flow of the hot water and the cold water. There's a solenoid two solenoids back there. I'll try to go get that. I actually got a set of those. If you got an ice maker on your refrigerator, it's got a solenoid back there where electrical current causes the solenoid, energizes the solenoid. It causes a plunger to move and turns on the water to your ice maker. So these are all over the place. Your electric locks on your car don't use solenoids because you got to unlock them and lock them. The problem with solenoids is they only create motion in one direction, and then we have to do something to bring it back. So normally a solenoid will have a spring on it. We put electrical current through these coils. It creates a magnetic field, causes the plunger to come into the solenoid, and then when you remove the current, then the spring causes it to go back. So that's very, very common on relays. So relays, either we mount them so gravity bring it back, or we have springs on them. So I don't know if we can show y'all those or not. Most of the springs are hidden. So these are electrically controlled switches. So relays are what actually started creating automation, where we can create something with little or no human intervention. So up until then, you had people that had to flip the switches and do all this kind of stuff, but relays allowed us to turn things on and turn things off electrically instead of manually. So this has added a lot of features. So this allows you to turn on your washing machine with a push button. Well, I guarantee you there's a relay in there. It allows you to turn on your microwave with a push button. Well, I guarantee you there's a relay in there that's doing that. It allows your thermostat to turn on your compressor for your air conditioner. Well, that little thermostat could not run your compressor, but it could pick up a relay or energize a relay to do that. So these are all over the places. So like the program controller couldn't run a motor. It might run a light, but it couldn't run a motor. But the program controller could energize a relay, and then the relay should run a motor. So this is a very, very important concept to understand. So these are solenoids. These are the solenoids, by the way, that if you ever took your washing machine apart, down at the bottom where your water comes in, this will be where it actually comes in. So this one of them will be hot, one of them will be your cold, and then this solenoid might let the hot water go out, and this solenoid right here might let the cold water go out. If you put warm, it would energize both things. This is a directional control valve where we use solenoids to control the flow of a fluid, like hydraulic fluid or pneumatic fluid. This is actually a solenoid right here. So we use solenoids all over the place to control the flow. And of course, solenoids, if we can combine a solenoid with contacts, we call those relays. So these are relays. So on this one, you can actually see the coil, and you can see the actual spring here. So we energize this thing, it would cause the contacts to close. So we have what we call control relays. These are not designed to run big loads. Then we have contactors. These are designed to run big loads. And then we have what we call motor starters. These are designed to run motors specifically. The problem with motors is they require a lot of current when you start them. We call them starting current. So when we set up a circuit breaker or a fuse, we have to size the circuit breaker to allow the motor to start. It's like your car. So you're at a standstill, and the light turns green. Well, you have to push the gas down further to get the motor in motion, get the car to start up, and then what do? Then you let up the gas, and of course you start shifting gears. So motor starters have sensors on them. So the circuit breaker or the fuses allows the motor to start, and then we have a sensor on it that if the motor stalls, we can disconnect the motor. So without popping the breaker. So we'll look at some motor. We got motor starters on the Amatro line, which got overloads, and we can show you that. So this is actually the operation of a relay. So you can actually see the contacts changing positions. You can't see, this is the actual coil that creates the magnetic field, which causes this to move. And one thing nice about current, if we put current through conductors, they create magnetic fields. So we have these things we call electromagnets, which I'll show you. I'll try to remember to get that up for the next class. So relays, a relatively low coil power can control much higher power through the relay contacts. The voltage applied to the coil, so we call that the coil. So we call this right here the coil, because that's all it is just a bunch of coils of wire. And then and it's all wound in the same direction. And then we'll usually have some type of metal going through it to concentrate the field. And I'll show y'all, I've got a little solenoid made up out of a drinking straw that I wrap wire around. And I'll jerk a nail up into it and show y'all. It's pretty simple. But everybody's seen electromagnets. You know, they show them a lot in movies. Even in James Bond, they had a helicopter. They had an electromagnet on it. Back when Sean Connery was doing it, I don't forget which movie that was. I think it was You Only Live Twice. And a big helicopter came up and dropped an electromagnet down and picked the whole car up. You see a lot of movies where they have the electromagnets in scrap yards and stuff like that, which is pretty neat. So the voltage on the coil and the voltage on the contacts does not have to be the same. So you could have a DC coil and you could switch AC on your contacts or vice versa. Relays allow one circuit to switch a second circuit, which is completely electrically isolated from the first, which is pretty neat. So we could have the output of the PLC might be 24 volts DC, and we could be switching, 240 volts AC, and the 240 volts AC is no way, shape, or form connected to the 24 volts DC. So your thermostat in your wall runs off 26 volts AC, but your compressor out there on your unit that runs your air conditioner runs on 240 volts AC. Well, you wouldn't want to put 240 volts coming up to your thermostat in your house, but they're completely electrically isolated from each other through that relay that's out there in your HVAC. The only disadvantage we have with relays is they're electrical mechanical devices, so they can fail electrically or they can fail mechanically. So my son just brought his control board for his dryer, I think, over to the house. It wouldn't work, and when he opened it up and tapped on the relay, it would work. So he bought the board. Was going to cost like $240, and the relay cost like $8. So he bought the relay, and he brought the circuit board over to the house, and I put it on there for him, and so it cost him $8 to get that fixed. My air conditioner, my heater just went out, and it was the relay. So relays are electromechanical devices. So just because my heat wouldn't work, because the blower motor wouldn't come on, and the heat was the gas would cut on, and it would everything would work, but the blower that actually blew it through the house would not work. And what it was the relay. So the relay, everything else worked. Thermostat was working, everything was working. The blower motor wasn't told to turn on because the relay that controlled it wasn't working. So if you know that kind of stuff, it'll save you a ton of money. So the difference between like $150 and $8 because it was the relay. Symbols of the trade. It's very, very important that you learn symbols. We're going to be dealing with electrical control symbols and also symbols that we'll use on our PLC. So learning these symbols are very, very important. So these symbols we'll use when we connect anything to the programmable controller. So anytime we connect something to the PLC, so if we want to connect a normally open push button, so a normally open push button, this is the spring-loaded push button, which means, okay, it's open until I press it. So open means it doesn't let current flow through it. So if current doesn't flow through it, it doesn't create any work. So a lot of y'all's got push buttons, like on your car. You might have, like I said, you might have a push button now that'll let you crank it. That's becoming very, very popular on on cars where you don't have a key anymore. You just carry this thing around in your pocket. You know, when you get a certain distance away from your car, you can leave it running, but when you get a certain distance away from your car, it'll automatically shut off. So of course, I think there was a story of one guy, died of carbon monoxide poisoning because he got out and left his car running, and he came in and threw his fob down on the sink, and it never got far away to turn the car off, and it got him. These are contacts. We'll talk about those a lot. This is called a normally open contact and a normally closed contact. We're going to have to do PLCs. It's a little different if you've had motor controls. So a lot of people say, which is easier to take, motor controls or PLCs? Well, if you take PLCs first, it makes taking motor controls easier. If you take motor controls first, it makes PLCs easier. So it'll help either class. So we'll look at these, and we're going to have to look at these a little different when we start talking about how we use these contacts inside a PLC program. Switches have what we call poles and throws. Poles is a number of switches that's being controlled by the same operator, and then the number of poles would be the number of positions the switch would be in to control the flow. So this symbol right here would be for a single pole, single throw switch. So it's only got one switch. So this is the wall switch. So a lot of times you'll go into Lowe's and you'll look at the switch and it'll call light switch, but it'll have SP, ST on there, meaning it's a single pole, single throw. This would be what we call a single pole. So we got one switch and we have two positions in it that can control the circuit. This is actually drawn wrong. This should come in here. So it's got one switch, one operator. This would be what we call a double pole, and each one of them controls one circuit. So that's a double pole, single throw. This right here would be a double pole, double throw. I haven't seen it drawn like this. Usually it's drawn like this, where they'll bring in one switch, and then they'll have this, and then they'll have another switch, and then they'll have the same thing, and then they'll come up here and put a dashed line, which means they're mechanically connected together. This would be what we call a double pole. So you have two switches, and each one of them can be put into two positions. This would be a double pole, double throw. And that's as far as we go. Once we get past double pole, double throws, then we move into something we refer to as a selector switch. Then we got some sensors that we'll look at. This is what we call a float switch. So you got a float switch in your commode, but it's not controlling the flow of electricity. It's controlling the flow of water. So when you flush your commode, if you ever had the top off, you'd see a float that would fall down, and then when the water raises up, the float would start rising, and when it got up to a certain point, it would turn it off. So that's a float switch. This is a timer, and we'll look at these at most contact because we actually have two symbols for this. We have this one, and then we have the same one, but instead of the arrow pointing in, the arrow is going to point out. But we'll look at these symbols when we get into timers. This is a pressure switch. So a lot of cars have this on it. So I've got a pressure switch on my car. My wife's actually has an analog pressure switch, so it actually tells her the pressure in all four of her tires, which is pretty neat. Mine, I got a Jeep Compass, and mine just turns on a light in my car that tells me one of my pressures are low. So there's a pressure switch mounted in the rim of the car that literally can tell me when I need to add air pressure to my tires. My wife's, she's got a van. It's a Chrysler van, Town and Country, but she actually can look at the readout that shows her the pressure in the tires. This is a flow switch. This would tell us when we've got a fluid that's in motion. And there's several of these guys, and we'll come back later on and look at some of these. So this would be devices that we would come in on our computer, which is a PLC. These would be devices that we would hook up as inputs to the PLC. So this would be like, the keyboard on your computer, a real computer, not your touch screen that you have on your tablets, or your this would be like most laptops have a true keyboard. That would be an input to the computer. Then we bring it in, it runs a program, and then it comes up and sooner or later comes to outputs. This would be an output. So this would be a relay coil. So we would connect this over here on the other side of the PLC where we have the outputs. This is where we would connect those items at. So light bulbs, relay coils, indicator lamps. These would go over on the output side. Solenoids, we don't show you the symbol of a solenoid. So this is the symbol of a solenoid. It's kind of like the symbol of a resistor, but a resistor goes out and has about 5 of these. A solenoid would only have 2, one up and one down. So that would be the symbol of a solenoid. I need to add that because you'll definitely run into those in PLCs. This is the relay coil. This is not the contacts. This is the relay coil. This would be the symbol that we would use to identify the contacts that are being controlled by the solenoid. And later on we'll show you how we can identify what goes with what. We'll actually let y'all look at a diagram for a print that was provided to us by U.S. Steel when we taught a class for them. And it's really, really good on showing you how we can identify what contacts are controlled by each one of these coils. But learning symbols are very, very important for the trade, because when you come up here on the PLC and you hook up a push button, then you need to draw the electrical symbol for a push button. If you draw a normally closed push, you need to draw the electrical symbol. If you hook up a limit switch, we'll look at the symbols for those also. We need to look at those, so we have a better slide or presentation on this than we do on that other one. So guys, let's go ahead and take another 10-minute break. When we get around an hour in class, we need to take a break, and we really need to do this on virtual classes. So I know y'all can get lost, and y'all have a tendency to work on other things while we're doing this and not paying much attention to us. So I'm going to go ahead and pause the lecture, and we'll take a 10-minute break, and then so we'll come back at 7:40. Okay? You need to get up, move around, do something for this 10 minutes. Go get you something to drink and just get away from this computer for a little while. This is the PLC that we got 2. We have this one right here in a little suitcase. This is the Micrologic 1000. This is a fixed PLC. And then we have the Micrologic 1100s, which we have enough of these for this class to use. So we'll all be on these guys right here. So that way I won't have to say on this one. It's a little different. They're basically the same as far as programming goes, but the way they have the inputs hooked up and the outputs hooked up. But what we do is you can literally see it. So on my computer, I have no idea how they have this keyboard connected to the CPU. And I have no idea how they got this display connected to the CPU. On this, though, we literally have to connect the inputs up. So what we're doing is we're going to simulate all these sensors and everything with these switches on the front. So these are connected to the input. So on this, these are all the inputs on here. So you have to electrically wire the inputs up. And that's one thing we'll look at. In this class, you won't wire the PLC, but you'll draw diagrams on how you would if you had to wire it. And then these are the outputs. Now, what's nice about this trainer is that one thing, we can put whatever PLC we want on it. So when we get to, well, if you take the 196 class, ILT 196 class, then we'll be taking these PLCs off and we'll be mounting the compact logic PLCs, and you will get an opportunity to wire actually physically wire the PLC. But we could do it here using banana plugs, because these are the outputs that's wired up here to the top. These are the inputs. These are the outputs right here. So these outputs come down to here. Each output's got an LED on it that indicates when the output is true. So we're not going to hook up a motor. I might hook up one and show you how this would work. But we'll say, okay, I want to turn on motor 1 after 5 seconds. Now, well, what would happen is an LED would come on, and this guy right here would go to 24 volts because it's outputted from the PLC. So we could hook up a 24-volt motor to this, or a relay. So this is the trainer that we'll actually be using. We're not going to use this semester. This section over here allows us to connect whatever PLC up here. It allows us to connect it up to the Festo line. You'll play around with this side when we get to if you take the ILT2.12 course. So if you take the 196, you'll actually be wiring a PLC onto this trainer. So we'll take this off. It's really, really cool. And then we'll let you wire up a compact logic. It's a 24EL, I think, that we'll be wiring up. And I'll show you all that. I'll show you the PLC. We won't wire it up, but we'll show you all the PLC that you'll be wiring up if you take the 196 course. This is the actual built-in power supply. I don't have it plugged in, but this actually powers the PLC. Well, actually, the PLC is powered up off 120 volts DC, and we'll talk about the different types of specs and stuff also when we get into that. I just made the PLC reset, by the way, and we'll talk about this display. I don't particularly like this display, but what's nice about a PLC is I turned on input 1, and it come up here and showed me. No, I've got it turned off. I'd have to plug that in. But it actually shows you when the inputs are true and when the PLC is. So this is what I'm doing when I'm sharing my screen, by the way. It's like a camera. So like I said, on the manufacturing line, you can actually see what inputs are true and what outputs are the PLC's output, and you can actually see it by these LEDs on the front. They tried it with this LCD screen, but most of the PLC now have gone back to the LEDs because they work out so well. So, some computer technician figured out how to wire the inputs up to the PLC and outputs on my computer. You're literally going to have to see. Here we'll draw how to wire them and how to hook them. We'll draw how they would be hooked up. So this is motor controls, but this is the language that we're going to program in. This is called ladder diagrams. And you can see why it got the name of ladder diagrams. So what we do is we have two power rails that here they're called an L1 and L2. So L1 is considered to be, in electricians, we would call this the hot, and over here this would be, the electricians would refer to this as the neutral. Odds are in DC this would probably be plus and this would be minus, but it might not have to be. And then what we do is we draw our circuits between L1 and L2. So this looks like the outside of the ladder, and then this circuit looks like a rung, and that's why it's got the name. So these individual circuits that runs between L1 and L2, these are referred to as rungs. So the main language used by PLCs, there's like 5 languages, and when we get into other sections, I'll show y'all the different languages that we can program some PLCs. But the main programming language over here in the United States is ladder. So we'll bring up our application, we'll create a ladder diagram, and it'll automatically give us L1 and L2, and then we'll draw our circuits between L1 and L2. So this is the way it works. So this is an actual relay logic circuit where we start off and we have a rung, and we come over here. So this is a simple series circuit. So we got one load, and then we have an overload. This would be, I know that this right here is what we call a motor starter, and we'll look at that later. And in between L1 and the load is where we put all our control devices. How you hook your control devices has nothing to do with what type of circuit it is. So this would be a basic circuit. It's got one load. This guy right here, this rung right here, has one control device, but it's got 3 loads, but they're all hooked in parallel. So these are the circuits we have. We have a single load series circuit or a basic circuit, or we have parallel circuits. We don't have any multi-load series circuits, and we have no series parallel circuits. So this would be a rung that's got 3 loads hooked up to it. This right here would be a rung that's got 2 loads hooked up to it. So what we do is we literally draw our circuits up between L1 and L2. And this is why, and it looks like a ladder. So we call this ladder diagrams, and the language is called ladder logic. It's called ladder, and we'll learn about logic. So we can use, with these control devices, we can do ands, we can do ors, we can do nands, we can do nors, we can do nots, or so that's the 5 basic logic functions that we have available to it, and we can do all those with how we hook these control devices. So this is called ladder. So these are called ladder diagrams. This would actually be a relay logic. We call this relay logic diagram. This is what you'll do in motor controls, and then PLCs. We'll start off by putting our rungs, and then we'll come over here and we'll put control devices, and then we'll come over here and we'll generate an output. But this is going to be a simulated output, and then we're going to connect that to something on one of our output ports. But the language we're going to use is called ladder logic, or ladder. These are all control devices. So L1 and L2, these are your 2 power rungs. Of course, inside the PLC diagram, it's just, there's not really power there. It's a program. But we still are going to create our programs between L1 and L2. And we're still going to call them rungs. It's extremely important to learn the symbols used in reference to the drawing of your chosen trade. It's also very important to learn the language of your chosen trade. So we're going to learn a lot of terminology in a class, and it's very, very important that you learn to speak the language of your trade. So when you go into that all-important interview, it's, can you talk to these technicians, and can you speak the language of the trade? The analogy I use is if I went into a doctor's office, and I went in to the doctor's office, and he looked at my elbow and called it my thingamajig, you got a problem with your thingamajig there, I would turn around and walk out. Or if he told the nurse, he put up 2 fingers and give him about this much, and he didn't say like, 15 milliliters, anything like that, then I'd turn around and walk out, because not that he wasn't probably the best doctor and it could have cured me, he just didn't know the language of the trade. So learning the language of the trade is very, very important when you go in and so if I had an instructor that was interviewing for electrical position, then I would want him to know symbols, and I would talk about him, the language of the trade. It's just like one of our guys come in for an interview for the job that Miss Bush got. And he was interviewing for that job, and what we do on our interviews is we make the instructors give us a sample lecture. So they have to give us a 15-minute lecture on a topic. We had one guy that chose transformers. And he said transformers step power up and down. Well, transformers don't step power up and down. Power in equals power out if the transformers were 100% efficient. Transformers don't create power, they just control power. So as soon as he said transformers step power up and step power down, then he lost the job because he didn't know the language of the trade. He didn't know that transformers step voltage up and step voltage down, but power in equals power out if the transformer was 100% efficient. So learning that is very, very important. I guarantee you. So we looked at work a little bit. Shorts are very, very important to understand when you wire these PLCs, how you hook them. And what's nice about a PLC, when you make a mistake like a short in your program or you make an open, then you're not going to cause things to happen. But a short is an undesirable path for current flow. It means you still have current flow. It just means your control devices is not controlling the flow anymore. A short circuit is when the source conductor and the return conductor come in contact with each other, and the only thing that's limiting the current flow in the circuit is the resistance of the wires. And that's going to be very, very low, but it's going to get there. And this is going to cause wires to burn up. It's going to cause insulation to come out. So short circuits are we want to prevent short circuits. So basically, if we use Ohm's law, it says if my R goes to 0, then my current would go to infinity. Of course, it can't. Something's going to give up the ghost. Either the wires are going to burn up, or your power source is going to burn up, or your power source is going to blow up. Somebody's going to give up the ghost when we have a short circuit. All circuits must have resistance. If it's not, according to Ohm's law, the current and power theoretically would go to infinity, which it can't. Of course, the current flow will never go to infinity. If the load is bypassed, the current flow in the circuit will be limited only by the resistance of the conductors and the internal resistance of the voltage source. So short circuits is what we protect against. So these are protected by overcurrent protection devices like fuses are used a lot. The big advantage of fuses, they self-destroy themselves, but they're a lot cheaper. Overcurrent protection devices like circuit breakers, we can reset them. So if they sense an overcurrent overload on your conductors, they'll trip or pop or whatever you want to call it. And we have the ability to reset it. But if you go down to Lowe's and look at a 15 amp fuse, a 120 volt fuse, and you look at a 15 amp circuit breaker, you'll see quite a bit of difference in the cost. So what's nice about circuit breakers is that we can reset them. What's nice about fuses is they're very expensive. So industries are probably going to have more fuses than they have circuit breakers. Short circuits, when current flows through resistance and electrical conductors, heat is generated. When metals are heated, the resistance goes up. Resistance goes up, more heat is generated. If something does not stop the current flow, then these conductors are going to melt themselves and they're going to cause fires. So you see a lot of times you'll see the news where they say this house caught on fire and it was an electrical fire. Well, what the problem was, it was a short circuit. So somewhere we had a short circuit, somebody screwed up, they didn't have the right circuit breaker in there, they did something with people find out they can replace circuit breakers. I've seen guys do it. So you can go to Lowe's and you can get a 15 amp circuit breaker and you can get a 20 amp circuit breaker that fits in the same slot. So they got a circuit breaker that pops all the time and they don't look for the problem. They go out and buy a circuit breaker that's bigger. Or they go out and buy a fuse instead. I got a fuse that keeps blowing. It's a 10 amp fuse. Well, by George, I can buy a 20 amp fuse that fits in the same slot. And then they burn stuff up. So that happens all the time, guys. So these are fuses and circuit breakers. You've seen all these. These are basically the circuit breakers you'll run into in industry or here at the college. College has a lot of circuit breakers. We have a lot of three-phase. We'll have a lot of three-phase circuit breakers here, AC. So circuit breakers, the only advantage a circuit breaker has over a fuse is that it can be reset once you let it cool down, by the way. A short circuit, so this would be a short. So a short would be like you lose one load. The only problem is now all the load will be across load 4. So usually what happens when you have a short is it usually causes other loads to go bad. But usually if you have a short, it probably won't blow a fuse. Insulators, we use insulators to prevent shorts, so we'll take a conductor and we'll wrap it with an insulator. It also allows us to handle the conductor without getting electrocuted, and it also prevents short circuits. So this is why when you look at all your extension cords or you look into any house wiring, you notice all these guys have insulators on it. An open, we create opens on purpose. So this is most people when they got a problem, they say they have a short. So my mom called it a short edge. I got a shortage somewhere, but it wasn't. It was just an open wire somewhere. So we create opens, but most people call them shorts. So common people don't understand the difference between an open and a short. And what they'll do is if they've got something that goes out, they say, I got a short in it. Shorts are bad. Opens might not be. Opens we create on purpose all the time. We don't create short circuits all the time. We don't create short circuits on purpose, but we do create opens all the time. Opens, so we create opens with our off switches. Fuses and circuit breakers create opens. Broken conductors, faulty splices. Splices when we have a conductor that's not long enough and we crimp it back together. So a lot of times when they'll have a break in the power lines, they don't replace the wire. They just go back and splice them back together. Termination is the act of bringing a conductor to the end. So the conductor has one function in life, and that's to get the current flow from the source to the load. Eventually, every conductor's got to come to an end. Bringing that conductor to an end, we refer to that as termination. We have crimp-on connectors. We have solder-on connectors. We solder wire into printed circuit boards. We have edge card connectors and all that other kind of stuff. These would be termination. So this would be an open. So we can have opens without open circuits. So this would be like our Christmas lights now. You lose one, we use one light. You lose the loads in that string because it's series, but your other loads are okay. So these are open. So that would be an example of an open. That would be an example of open. That would be an open. That would be an open circuit. So to get an open circuit, you have to break the wire or open the circuit, open the conductor between the voltage source and the first load. So that's why your light switches are before the loads. You know, all your control devices are going to be on the between L1 and the load. So open that would be an open circuit. Voltage across the source is going to so voltage across an open will measure the applied voltage. Voltage across the short will measure pretty close to zero. So if you check a fuse is supposed to allow current to flow through it. So a fuse, if you check it with an ohm meter, it should have almost 0 ohms worth of resistance. It should drop 0 volts. So if you put your voltmeter across a good fuse, it's going to measure pretty close to 0 volts. It's got to drop a little bit of volts because that's the way it blows. If the direct current and alternating current. So we'll look at this, guys, and then we'll call it quits for the night. So DC flows in one direction. The electrons in a DC circuit flows from negative terminal to the positive terminal. So this got people confused for a long time until they realized what was actually moving. So electrons are moving. So the negative terminal repels the electrons through the circuit, and then the positive terminal brings it back. So electrons through the circuit moves from negative to positive. We call that current flow. There is another method called conventional current flow, which was the original way they thought current flowed, from positive to negative. But after that, they figured it out, and so here we teach electron flow, if anybody knows. So DC is produced by DC generators magnetically. Batteries produce it chemically. Thermocouples, these are sensors. These produce it by heat. Solar cells produce it by light. Piezoelectric devices create it by force. Electronically, these are what your power supplies you have. That like your cell phone, when you charge your cell phone, your TV, electronic devices operate off of DC, by the way. And what the big advantage of DC is that we can control it electronically. So electronic devices operate off of DC. Even if we've got an inverter in our car that takes DC and switches it, makes it AC, it operates off of DC. So that's the big advantage of DC, is that we can electronically control it. So your TV operates off of DC. Your cell phone operates off of DC. Everything in your car operates off of DC. So you have an alternator in your car, but we convert it to DC so we can electronically control it. So that's the big advantage of DC. So this is some devices, DC cells, batteries, DC generators, solar cells, piezoelectric, thermocouples. So these are just some pictures of the devices that make DC, that create DC. These would be the sources, not the load. This would be the source of the voltage that causes current to flow in one direction. Alternating current, these guys constantly swap direction. The voltage source in an AC circuit constantly swaps polarities, which causes the current to change direction. It's less expensive to generate. It's extremely efficient to transmit power over long distances because the voltage levels can be changed with transformers. So that's the big thing right there. I is equal to P over V. The power company is trying to give you power. So the higher they can make that voltage to transmit it, the lower the current required to send that power. So that's why they step it up real high for power generation. So on some of these high tension lines, they're running like 750,000 volts. So that means they could send 750,000 watts of power with 1 amp of current, which means now the resistance in my wire is not going to drop as much voltage, which means now instead of using copper, I can use aluminum. Aluminum is less expensive and it weighs a lot less. So these big old towers that supporting these high voltage lines don't have to be as sturdy. But the problem is 750,000 volts would vaporize you if you got in contact with it. So what we do is the closer we get to you, we start stepping that voltage down. As we step the voltage down, the current to deliver the power goes up. So the conductors have to be bigger. So this is why you have two voltages at your house. So the two voltages we have is 120 volts AC, and we have 240. All your high power devices, I'm not saying all your high power devices run off 240. So we can run smaller conductors to get that power out to those devices. So now we can run the wires through the wall to run our air conditioners outside because they run on 240. Right, so all your high power devices run on 240. All your low power devices run off 120. So all your wall outlets are 120. These are your low power devices. So so that's what you need to understand is the higher we make the voltage, the less current's required to produce that power. So look at think about all your high power devices. If you got an electric water heater, runs off 240. If you got an electric heater, runs off 240. Your clothes dryer runs off 240. Those plugs are mounted down on the floor. So if you wanted to pull out your washing machine, you notice your washing machine plug is in the back. You can actually get to that because it's 120. Your 240 plugs have to be mounted down on the baseboard behind the equipment they power. So you can't easily get to those plugs because they're twice as dangerous, actually 4 times as dangerous as 120. So the higher the voltage, the less current required to produce that power, but the more dangerous it is. So over in Europe, the only thing they have is 240. Over here, we have 2 voltages in our houses. 120 is a lot safer than 240, even though 120 can kill you, but it'd have to catch you in a certain situation to get. So some of y'all's probably got shocked by 120, and you're still alive to take about it. So AC alternators produce generators, but in our car we call it a alternator electronically. By the way, over here on this one, I should put you out there. We create DC. So our body chemically creates DC. Our brain processes DC. So your body actually creates that. So bioelectrically, we create DC bioelectrically. AC, the only thing that I know that creates AC bioelectrically is electric eels. But what we can do is we can change the voltage level with transformers. So we can step it up for transmission and step it down for safety. And that's the biggest advantage of AC. And AC motors can run off induction. So AC motors, induction motors, are a lot less expensive per horsepower than DC motors. But they're harder to control. So automobiles, we have our alternator, mobile AC generators. I bought me one of these when the snowstorm of '93, when we had 13 inches of snow and power was out for a while. AC generators, this is actually the big generators that they're running at a power station. An electric eel actually outputs AC and DC, which is pretty neat. It outputs DC to kill things, and it outputs 10 volts AC at about 25 cycles per second to stun things. A lot of people have these in their cars. My wife has an inverter in their car. It electronically takes DC and generates AC. And then here you'll deal with these things called function generators, which electronically generates AC for us. So when you get into solid state, we'll deal with these, and also in AC, you'll deal with a function generator. Most alternating currents provide the voltage source changes direction at a constant rate. This repetition produces a voltage waveform shown on the next slide. An AC waveform is referred to as a sine wave because it varies with the trigonometric sign of the voltage. So some of y'all might take trig, but some of y'all might have had it in high school. But this is what we call a sine wave. So it's generated on a circle. And so if we could stop this thing, oops, let's see if I can do it like this. No, it don't stop. Wow, that's interesting. Let's do it this way. No. But if we could come up here and stop this and drop a perpendicular, we would generate a right triangle. Right triangles deal with calculations. One of the calculations is called a sine. So this is called a sine wave because the voltage varies with the sine of the electrical angle. It's generated on a circle, so there's 360 electrical degrees per sine wave, and that's about all we need to talk about. But this is so if I was to take a device called an oscilloscope and hook it up to Alabama Power, we would see this waveform right here. So cycles, one repetition. So this is a repetitive waveform. One repetition is called a cycle, and then the rate of the cycles is called the frequency. So Alabama Power, the frequency for us in the United States is 60 cycles per second. Over in Europe, it's 50 cycles per second. So the cycles per second sets the speed of an AC induction motor. So over in Europe, it would run a little slower than it would over here. By the way, just like watts and volts and stuff like that, most of the people who are fundamental in the development of a physics trade get the honor of having their name assigned to this. So normally this will be referred to as hertz, which stands for cycle per second. So y'all learn that when you get into. So over here it's 60 cycles per second. By the way, to transfer through a transformer, you have to have AC. And when we come into class on the 26th, I'll actually show you how I've made a transformer. I was just coiling wires together. It's really cool. So this is something we probably don't need to know. So 60 cycles, we're going to deal with AC. AC and DC are not the same. As you can see, the work I get is not going to be equal to this. The work I get is not going to be equal to this. The work I'm going to get is going to be not an average, but somehow I'll have to calculate the equivalent work that I'll get out of that. So you'll learn that in AC. So when I say it's 120 volts, uh, actually from here to here, if we measured that, would actually be around 340 volts to get 120 volts out of work out of it. So you don't get the 170 volts positive peak and 170 volts negative peak, because it's only at that for good gracious, for something that we couldn't even understand, maybe picoseconds. It's only at that peak for no time at all, and then it actually drops to zero. So this guy actually drops to zero 120 times a second, and it's very, very precise too. Used to, when we set the speed on the old floppy disk, it had a strobe wheel on the back, and we could literally put it under fluorescent lights, and we could adjust the speed till the strobe stood still, which means the fluorescent lights are flashing at the same rate. So fluorescent lights are actually flashing. So this is why you have to compensate for fluorescent lighting, or your pictures are turning out yellow looking. So your camera, and this is why a lot of times you'll have a shirt that'll be one color when you're under fluorescent lights, and you go out in the sun, it'll have a different tint to it. My wife's got a purse that she thought was red, but then she got it out in the sun and found out it was pink, which was pretty interesting. So AC versus DC. AC is constantly changing directions. Voltages can be stepped up for high wattage loads. AC motors are less expensive. DC current flows in one direction, can be electronically controlled, and it's easier to produce. We can produce it chemically. There's all different type of ways we can produce DC. AC usually has to be done either electronically, or it's got to be done mechanically. So AC basically doesn't exist in nature. The only thing I know of that produces AC is an electric eel. How it does it, I haven't got the slightest idea. I read about it one time, which is really, really neat. And guys, this is about it. So when we have a PLC, so this is going to be one thing, and you're going to have to know when you buy a PLC is what powers the PLC. So this PLC is powered up off of AC, and it's got an internal DC power supply. If it'll focus, it's called DC out. So this guy's got a power supply built into it that takes this AC and runs this DC. These inputs are DC inputs. Of course, the problem is that this power supply here doesn't have a high enough wattage rating to run a bunch of sensors. So what we're doing is we actually run this off the power supply that's inside the trainer, that's taking 120 volts AC and converting it into 24 volts DC. So 24 volts DC is a very, very popular voltage used by a lot of PLCs. One reason is that it's well below what's considered to be the lethal voltage level. For a lot of times, there was no definition on what voltage was lethal. The National Fire Protection Association, or NAFTA, finally came out. They're the ones that wrote the National Electrical Code, which most people call it NEC, that electricians have to wire houses by. National Electrical Code is in there to protect the equipment. There's really nothing inside that code that protects you. So eventually, NAFTA came out with a code we call 70E. 70E it's a code that protects you. It protects you against electrical shock and then arc flash, which should be when we have a high energy short circuit. It creates a flash that's hotter than the sun that causes things to melt. NAFTA has identified 70 volts as the lethal voltage level. So as soon as you get above 70 volts, you got to start wearing special PPE. Now PPE, I used to have to tell everybody what PPE stands for, But since COVID came out, everybody knows now that PPE stands for personal protective equipment. So below 50 volts, you don't have to wear near as much PPE that you do as soon as you get above 50 volts. Then you got to start adding PPE, and the higher voltage and energy you have available, pretty soon you'll be wearing bomb suits to work on this kind of stuff. So what has happened over time is PLCs basically operate on 24 volts DC, which means now if I'm at 24 volts, it means on the PLC side we can operate on very little PPE to operate on these things. But as soon as I get up to 50 volts, then we got problems. So we could take these outputs. We could have one cabinet that's got all my PLC in it. Then we could take these outputs and run it into a power cabinet that's got all the power stuff, and that's where we would have to protect ourselves real easy. So one of the primary voltages for inputs and also outputs is 24 volts DC. So that's very popular, and we'll talk a little bit more about that as we go along. We'll also talk about these lights. We'll also come up here and talk about these indicators that this PLC is going to give us to help us troubleshoot if we have any problems. And then, of course, we'll look at the connection of the PLC. Like I said, this semester you're not going to connect it, but you're going to draw how it would be connected. So drawing your symbols just like you would do it, and we'll look at some diagrams. We'll look at some of the wiring diagrams for the Amatro line, and we'll look at some of the PLC wiring diagrams for the Festo line. We have all that information available to us. So what we're going to do next class is we're going to skip over to Chapter 3 because it'll be a lot easier to do virtually. I like to show all this stuff, and right now all I can do is just put a camera up and show it. So what we're going to do next class, by the way, there is a topic quiz on this, is we're going to jump into, I can keep sharing my screen. We're going to jump down into Chapter 3. And this is in your book. So if you have your book, it's great. It's Chapter 3 in the book. But like I said, the PowerPoint slides should tell you enough. So what you probably need to do, that's not Chapter 3 book, Rich, is you need to go into Chapter 3, which is called Numbering Systems. And it's got the PowerPoint slides out here. So you can go ahead and start looking over the PowerPoint slides. The PowerPoint slides are pretty much in detail. So the problem is that numbering systems are basically how we represent numbers. Computers, we know the decimal numbering system, which we have digits 0 to 9. Computers don't know the decimal numbering system. PLC don't know the decimal numbering system. It uses a numbering system called binary. So to understand PLCs and understand the way they are, then we're going to have to look at different types of numbering systems. Of course, most of the time the PLC will take care of you, and it will display things in decimal, and it'll let you enter stuff in decimal, and then it converts it with an application that's built into the operating system. But when you get into doing logic like ands and ors and creating masks and compares and that kind of stuff, then you're going to have to understand binary. Setting up IP addresses, understanding subnet mask. The predominant method of connecting PLCs together now is something called Ethernet IP. Some of y'all might not even know. We'll discuss a little bit in PLC 2 or 196. We'll learn about networking. We'll learn about IP addresses. We'll learn about Ethernet IP. How we can connect PLCs together to share information. So here, like I said, basically this is primarily programming. And like I said, the furthest we'll get in this class is up through counters. So we'll get through timers and counters. But like I said, this has got all that information. You can go ahead and start looking over it and figuring it out. And then there is a lab on this. But what I'm going to do is I'll try to do that this weekend, is I'll set it up as a test inside this chapter. So instead of turning in the lab, you can actually go in and do it, because all it is converting between numbering systems. And I'll go in and set that up so you can be able to do one lab from home. And then, of course, then on the 26th, we will be on campus, guys. We will be on campus on the 26th. And since there's only 8 people in the class and we got a nice big classroom, we can social distance really, really easy. Everybody's going to have their own PLC. So we're going to start meeting. We'll meet on campus unless something else comes up, and then we might have to, depending on what the Alabama college system decides, we might have to drop back to virtual. But we'll see what happens. So any questions? Okay, so we got 2 people didn't show up. I'll try to figure out who those are. So I've got Mr. Kirby's here, Henderson's here, Brown is here. Kyker, how would you say that? Kyker? Kyker. Okay, I got it then. Mr. Thompson here, Addison's here. I think that's that's the 6 that's here, and I'll try to figure out the 2. If you know the 2 people that's not here, y'all know y'all can click on that thing and actually see who's over here. Those 3 purple arrows on the side, and then click on participants. If you know somebody that's not here, you need to have them get in contact with me, because I don't know what they're going to do. So. We're supposed to hold class the first class, but this is recorded, so I'll get it uploaded this Friday, and I'll just let them know. But Thursday's class, of course, will be virtual, and if you got any Monday, Wednesday class, remember Monday the 18th is a holiday. We will not meet, or classes will not meet on that day. So if y'all ain't got any questions, guys, that's it for the night. If you got any questions. Even if I'll hang around a little while inside the collaborate room, if you got something, personal you want to talk about, I'll hang around and answer y'all's questions too. Hope y'all stay safe and stay out of trouble. Okay? All right. Bye-bye.